I suppose you want to hear another joke. Right, so I just want to give you a hint of this. This is work I've been doing with two people in Newcastle, Juan Carlos Aguero and Ramon Delgado, those who know Newcastle. And we've been trying to look at rank-constrained optimization. Now, what's an example of a rank-constrained optimization problem? By the way, I'm not going to go on very long. Let me preempt what I'm going to say is that if you find this interesting, then you should seek medical advice. So I got the joke after all. Okay, so if you find this interesting, then you're probably doing some optimization, tough optimization problems where you think there might be some difficult constraints. What I suggest is that you write to me and I'll send you the presentation. It's got some of the background in it, and also it's got some references which are much more important. So I'll send you that. Or I'm going to send it to Eduardo as well. So if you'd rather have a Brazilian contact, then Eduardo will also have a copy in a few days' time. And then if you want to ask me about it, you write to me, and I'll pass the question on to Juan Carlos and Ramon, of course. That's the way it works. Okay, so what's all this about? It's about the following problem. I think I might back up a little bit, and I'm not going to give you the full details. I'm going to stop short of the end. In the first part, regularization is sort of an ad hoc way of adding constraints by saying what things you don't like, but it's sort of a bit heuristic. But rank-constrained optimization is asking, can you solve a problem with a hard constraint of, for example, the rank of a matrix? Now let me give you an example. Now I know this is technical, but I hope those who stayed want technical stuff, right? This is to whet your appetite for dinner. So here's the question. Say I ask you to estimate the impulse response of a system. Hey, that's easy. But then I tell you that the system has Macmillan degree 3. Okay. So how do you describe... So this is state space model. Xk plus 1 is A, Xk plus B, UK. YKC, Xk, and we know that the impulse response is given by C raised to the AI to minus 1 times B. All right. Momento. Okay. That's teaching me Portuguese. It's good. So if you write down this matrix, which is shifted impulse responses, you know that this matrix can be written as the product of this matrix and this matrix. And if you've studied postgraduate or undergraduate control theory, you'll know that this matrix is called the observability matrix and this is called the controllability matrix. And that if the system has got Macmillan degree n, then these two tall and wide matrices have got degree n, and so this Hankel matrix has got degree n or r. So then what you can do is just ask the following question. Estimate the impulse response subject to the rank of the Hankel matrix, which is this funny matrix you form from the impulse response being 3. And that's a tough problem, but what I'm going to show you is a way of that you might solve such a problem. You all interested? If you're not interested, you should have left with the rest. It's too late. So this is how you might set up mathematically this problem. You might ask, let me minimize some function like a least squares cost function, finding the impulse response of the system, subject to the rank of the Hankel matrix being less than or equal to 3. Now this is essentially an impossible problem, right? Because rank constraints are even worse. A version of a rank constraint is a cardinality constraint, counting parameters. Why? If you take the parameters of a system and you put them in a diagonal matrix, theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7, up to theta 1000. And then I want to have just 3 active parameters. Then all I need to say is that diagonal matrix should have rank 3. Because that says that there's 3 parameters that are non-zero, all the rest are 0. I'm not telling you which ones, I'm just saying that 3 of them are non-zero. Tough problem, because this is one of those combinatorial questions. So an example of a rank constraint problem is when you tell me that there's 1,000 potential parameters, but only 3 of them are useful. But I don't know which 3. Now if we can solve this, we can solve that one, maybe. Where's one colour? So he could do it. All right, so the first observation is that having rank less than or equal to R is equivalent to the existence of an orthonormal transformation matrix W, such that when it operates on this, you get 0. Now, this matrix is a special matrix in that it only selects n minus R elements from the space spanned by the matrix. So if you think about it, if the rank is R, there are n minus R combinations that are 0. So what this says is that if you can find that it's equivalent to finding a matrix which, when multiplied by g of theta, selects all the bits that project onto 0. And of course, everything but R things project onto 0. So you can see that somehow that this is equivalent. So what you've done is to convert a difficult problem into a somewhat manageable problem. I heard Ramon Delgado, my student, give a talk at the IFAC World Congress in Cape Town. And he said, this is fantastic. This takes a extremely difficult type problem and converts it into a very difficult problem. So that's what he said. But this looks a bit more manageable because now it's a bilinear constraint. You've got a matrix multiplied by another which should give 0. But still, this is a multivariable constraint. This is called a Fan-Tope constraint after the person who discovered this trick. But if the matrix G is positive semi-definite, so if you take the Hankel matrix and multiply it by its transpose, you get a positive semi-definite matrix. And now you can assume that the matrix you're dealing with is positive semi-definite. And then having this equal to 0 is the same as the trace of this being 0, because this being identically 0 in the positive definite case says that if you add up the diagonal elements, which is the trace, you'll get 0. So now we're getting something that is quite manageable, because we've taken a cardinality constraint or a rank constraint and converted it into a quite simple bilinear rank constraint. So this constraint is not trivial, it's not convex, right? It's not convex, so it's bilinear, but it's a lot easier than a cardinality constraint. So this is a big advance, I think. Right? Okay, so then you can start asking questions. Does there exist a matrix in a bucket that has rank G? Can we find one? Because after all, if you're trying to do optimization, you better at least have one matrix that is of that rank. And you can answer that question by doing a minimisation over the bucket of G's and a minimisation over these orthonormal transformations. And if you get 0 for the answer to this problem, then you know indeed that there is a matrix of rank less than or equal to R. So you can see, as Ramon said, you convert a very, very, very difficult problem into one with bilinear constraints, but which is still manageable. Right. How am I going? I can't seem to go past slide 82. Oh, so I need to point over there. Now, in the case of a positive definite matrix, the finding of a W, if I give you a G, what's the associated W that gives you 0, is really easily found. What you do is a singular value decomposition of G, and then you form W by the singular vectors. And you just choose those which span the 0 singular values, and you've done it. Kind of makes sense if you know about linear algebra. Right, so this is actually easy. So what you've done is to convert one of these rank-constrained optimization problems into a double minimization problem in which you've got this bilinear rank constraint. Now the bilinear constraint is not convex, and so you've got to use tricks. And I'll show you two tricks. One is an iteration. Do I keep the iteration? No, I didn't. Okay, one is an iteration. One is an iteration where you guess G and find W. That's easy. I showed you that's just an sort of an eigenvector problem. And then given W, you find the best G. So it's one of these sort of iterations, like the EM algorithm. It only converges to a local minimum, but our experience with it is that it works very well. So here's something you can code very easily. Find W, find G, find W, find G, find W, find G. And you can solve these very difficult problems. Okay. I'm going to do this fast. It's like EM. You can also get global strategies by using branch and bound. But in order to do this, you've got to have upper and lower bounds on the solution. But then you can get globally convergent algorithms. All right. So let me give you a couple of applications. I'm doing this fast. But this is a very well-studied problem in econometrics. Econometrics, yes. Okay, so here's the problem. You measure a lot of financial variables. I don't know if anybody knows about this problem. A couple of people who are famous for working on this, one in particular, the control theorist might know, is Manfred Deisler. Another one who's done a lot of work on this problem is Brian Anderson. Right. This is called factor analysis, so let me give you the idea. Just the name is interesting. I'm not going to be able to tell you about factor analysis for all sorts of reasons. One is I don't know all that much about it. But I can give you the idea. Here's the idea. That you measure a whole lot of economic variables, right? Hundreds of economic variables. Well, what you believe is that throughout the world, that it's all driven by a small number of factors. Right, so if you want to get a feel for it, you might measure 100 economic variables throughout the world, but you believe that down there in the model somewhere is 3 things that are driving all that. Right, so this is the factor problem. And or another one who's worked on this problem, by the way, is Rudy Kalman. A lot of people work. Okay. But you must know that there's much more going on than that. So we also have variables that affect all of the 100 things, but they're more local in nature. So if you look at the Brazilian economy, then there are things that are affecting your GDP, but they're not affecting the Australian GDP. But there are things that are affecting the Brazilian GDP and the Australian GDP and the European GDP and the Indian GDP. But those common things, those common variables, are small in number. This is the hypothesis, right? And we might hypothesize some number, 3. I'm always using 3 as the example. And you can ask me afterwards, why not 4? I don't know. I'm not an economist. But let's say that there are 3 things that drive the world economy, but there are local things as well. Okay, so let's look at this a little bit more detailed. So there's a common part which are global influences which are small in number, and there are things that are called idiosyncratic components which just affect the local variables. Okay, so let's try and put a mathematical formulation on this. We can measure the joint covariance of all the variables. And basically the assumption in factor analysis is that you can decompose the covariance matrix into 2 terms. These are the local terms, which only if... So this matrix is sort of diagonal, and this is a tall matrix times a fat matrix. So this thing in here has got rank 3. So this is 100 by 100. This is 100 by 100. You can assume it's diagonal, for example, and this matrix 100 by 100, but has only got rank 3, because there's only 3 things that underlie this thing. So this is the problem of factor analysis. It's well studied in econometrics, and if you haven't heard of this problem before, then that's something I've told you about, factor analysis. And I've saved you going to one of Brian Anderson's plenary addresses at CDC a few years ago, where he gave the plenary address on factor analysis. Gave a very good talk, by the way, on exactly this problem. Okay. So there are various ways that you can address this problem. If you assume that the noise, the idiosyncratic component, is a diagonal matrix with the same number on every diagonal, then the problem has a very simple solution, and it's called principal component analysis. So that's something that if you're a chemical engineer or you would have heard of. Principal component analysis can be applied to this problem, but you need to have the same variance. If you have a diagonal matrix and it's has different elements, so different variants for the idiosyncratic components, you can use the EM algorithm. And I think that's what Brian talked about in his talk, applying the EM algorithm. But what if I told you that the noise covariance was just sparse? Then we can put all of the components in my talk together and do sparse estimation with a rank constraint. So what you do is you measure the covariance matrix. If you were to subtract the noise component, then you get a matrix which has got rank 3, right? Because you're left with the covariance of the factors. So this is an example of a rank constrained optimization problem. And I've got a simple example where you have 20 economic variables, 3 factors, that you take 100 measurements over time, that the matrix is diagonal, that the noise is not diagonal. Noise is not diagonal. And this shows you the true covariance of the noise. It's not diagonal, but it is sparse. And this is the application of this algorithm to show you that it worked. And this is principal component analysis. As I said, principal component analysis assumes that the diagonal elements are all the same of the noise, and the matrix is diagonal, and this is EM, which basically allows you to have different variances. Okay, and I want to finish with the problem that I motivated this with. You're not going to follow everything I said. I know that I can't follow it, so I don't expect you to. But if you're interested and you've got a problem that is of this nature, read the references. There's a lot going on in statistics and optimization theory about this problem, and maybe there'll be an opportunity. Okay, but I want to return to the original problem, which was how do you estimate the impulse response of a system if I tell you that the rank of the, what did I tell you? The rank of the Hamiltonian matrix is 3. I can do that. That's the setup. You do least squares on the impulse response, but with the constraint that the rank of the Hamiltonian matrix is less than or equal to 3. This was the underlying system that we assumed, so it does have Macmillan degree 3, and just to show that all this works, these are the true singular values of the Hankel matrix. You can see that they're definitely 0 after 3 because it's a third order system, and this is what least squares give you. This is rank constrained optimization. You see it's a constraint that you only have 3 non-zero singular values. Question, why is the cost higher than for least squares? Come on, there's a question I can ask you. Why is the cost higher than least squares? Do you know? Look, it has to be. This is fitting an elephant to anything. Least squares gives you the minimum cost. Full stop. No questions asked. It's the minimum least squares cost. If you say, oh, hang on, I'm not interested in the least cost. I'm interested in the least cost, but it's got to have Macmillan degree 3, you must get a worse fit to the given data. Yep. Now this is not surprising, but you see you've injected some real information into the problem. So the model you get may be better for prediction. Yeah? Because just getting a good fit to pass data, you could be subject to overfitting. But if you constrain the Macmillan degree to be 3, which is a real piece of prior information, then you get a higher cost for the least squares cost function, but the model may be inherently better in terms of prediction. Does that make sense? If you followed that, you've understood the whole talk. And what else is on here? Oh, this is another thing that another algorithm that's getting a lot of press lately, called the nuclear norm. Again, if you're working in this space, there's a lot of papers coming out on the nuclear norm. What's his name? Stephen Boyd and others are working on nuclear norm. Okay, so this was really just to give you, to whet your appetite. I know we're out of time. If you want to know about rank constraint optimization, I'll go to it. There's lots of papers that you can read. Write to me, I'll send you the copy of the slides which gives you the references. I'll send you the papers, the little first papers that we've written, and then you can have fun yourselves. And again, hey, thank you for staying back, it's amazing. Right, that's it, good night. Right, go home. Unless you got a question. Any questions? Any questions? Right.
Do you also work with machine learning problems?
So I didn't. The last thing I didn't hear.
I want to know if you have applied any of these rank constraint optimizations with machine learning problems exactly.
Not. Yeah. So the question was, do we have a version of our work for machine learning? Yeah. I think it's directly applicable, but I don't have a paper that directly addresses machine learning, but I think it's a great opportunity. Yep. Okay. Yep. It's a quintessential example, question in machine learning, I think.
Have you thinking about bringing your lecture, making associations with machine learning?
Yeah. I think it's a perfect question, and I think it's something that should be explored. I think they're using nuclear norm in machine learning, but I don't think they've got onto this stuff yet, so there's an opportunity for research.
I've seen some papers about max norm and trace norm.
Yes.
But they aren't explicitly limiting the rank of the mate.
Right, so the trace norm is sort of crucial to all this study. So those papers would be getting close to the thing we're talking about. Yep. Yep. Obviously know a lot about it. Any other questions before we do what we need to do?
To do ECA with threshold,
Oh.
achieve the same 3 parameters.
That's a good question. What about principal component analysis where you do thresholding? That would give you the 3. You're dead right. I don't know. How do you choose the thresholds? I've got to have a defence. How do you choose the thresholds? I don't know. That's a good question too. Yeah. Okay, other questions? If you're particularly interested, if you write to me, I'll put you in touch with Wayne Carlos Aguero, who is looking at issues with machine learning and this problem. I don't think he's made all that much progress yet. So, okay. All right. Good night.